In this program, we aim to raise your awareness and understanding of low adhesion conditions and the effects they can have on train handling. Most of you have, at one time or another, experienced driving in these conditions, and you'll know just how important it is to identify where and when such conditions arise, so that you can adapt your driving technique accordingly. We'll explain what low adhesion is, how you can anticipate it, and what to do when you encounter it. We'll also look at some recent developments and explain what steps are being taken to manage this problem more effectively, including the formation of an adhesion working group. Let's start by looking at the instance which occurred in 1994, either wholly or partially as a result of low adhesion conditions. During the year, there were 91 signals passed at danger, 7 collisions with buffer stops, 1 collision with another vehicle, and 503 station overruns. The most serious of these incidents was the buffer stops collision at Slough last autumn. Fortunately, there have been no fatalities arising from low adhesion related incidents, but many injuries have been caused, as well as damage to track and vehicles and, of course, service disruption. So what is low adhesion? Starting and stopping a train relies on the ability of the wheels to grip the rails in order to transfer the traction or braking forces being generated. This is no different to your car, which relies on the grip of the rubber tire on the road surface during acceleration and braking. In railway terms, the amount of grip between the steel wheel and the steel rail is known as adhesion. This can best be considered as a measure of slipperiness. The adhesion available varies considerably from extremely low levels, when the rail is severely contaminated and therefore very slippery, to very high levels, when the rail is clean and dry. Before we look at the levels of adhesion necessary to start and stop a train, we need to consider how the adhesion level is measured. The technical term is mu, and it's normally written as either a decimal fraction, for example 0.1, or as a percentage, for example 10%. We'll use the percentage term for the sake of simplicity. To start a train on full traction power can require an adhesion level of up to 25%. To stop a train using a full service brake application requires an initial adhesion level of between 6 and 9%, depending on the type of brake system. In addition, modern multiple unit trains with enhanced emergency braking require an adhesion level of 12% when the emergency position is selected. From this you can see why trains are often harder to start than to stop when the rails are contaminated. Almost 4 times as much adhesion can be needed for starting than for stopping. However, if you experience trouble in starting, there's always a risk of a problem when braking. Don't forget that wheel spin can also cause track damage and may need reporting in accordance with the rulebook. Where possible, avoid wheel spin in low adhesion conditions by applying traction power more gradually. If we look at the graph which shows in general terms how frequently various adhesion levels occur, we can see that there are times when the levels fall slightly below the 6 to 9% range needed for full service braking. This is the yellow area. We can see that these conditions occur relatively infrequently, and for the purposes of this program, we'll call them normal low adhesion. On very rare occasions, extremely low adhesion levels occur, the red area on the graph. We'll call these exceptionally low adhesion conditions. The large green area represents the frequency of conditions that are well above the 6 to 9% range needed for full service braking, and we can readily see that these conditions exist most of the time. So what are the causes of low adhesion? It's a product of rail contamination, which may be caused by naturally occurring weather conditions or by local environmental or industrial conditions. Some of the causes, like leaf contamination, may be obvious and well known, while others, like industrial pollution, are not so obvious. They all have the same effect, however, and that's to reduce the level of adhesion, which sometimes results in extended stopping distances. Once again, look at the comparison with your car. Stopping on a dry road isn't a problem, even when you brake heavily. When the road surface is wet or greasy, it's a different story. You need much more distance to stop without skidding. If the road is covered with snow or ice, it's very difficult to stop the car at all. Exceptionally low adhesion may be viewed as the black ice condition on the road, an unseen danger to the unwary. So how do you know when and where low adhesion conditions might exist? Many locations are well known, but do you know where they are on the routes which you work over? Here are some common examples. Known leaf fall sites. During the autumn, fallen leaves are swept up and crushed onto the rail by passing trains. Coastal lines where sea spray settles on the rails. Industrial areas where pollution from nearby factories or particles such as coal dust or sawdust can contaminate the rails. Cuttings which are shaded from direct sunlight tend to trap moisture. Low adhesion can also be caused by particular weather conditions which can happen anywhere. For example, damp autumn mornings where the rail has a light film of overnight rust, or where the dew point is reached in the late evening. Light drizzle reduces adhesion, so does the first onset of rain after a dry spell. Quite apart from industrial and weather-related conditions, there are other less obvious causes such as fuel or oil spillage from locomotives, multiple units, and even aircraft. Defective flange lubricators can deposit grease on the railhead, and agricultural debris spilled at farm crossings can be unexpected adhesion hazards. A good clue to the likely presence of low adhesion is wheel spin when starting or accelerating at speed. WSP activity is also a good indicator. So is erratic speedometer behavior. What can be done about low adhesion depends on the nature of the contamination and whether it occurs at random, such as with climatic conditions, or whether it happens regularly at specific locations and at specific times, such as with leaf contamination. Normal low adhesion, which arises from everyday causes like the onset of rain or drizzle, usually disappears as suddenly as it appeared. It's almost impossible to prevent this by remedial action on the part of the engineers. The much rarer exceptionally low adhesion, such as that caused by crushed leaves, fuel, oil or grease, can be dealt with by rail cleaning or sanditing. However, in all cases, one of the most important parts of the solution lies with your driving technique. We'll come back to that in a moment. You'll be aware that there are programs to control line-side vegetation growth and to treat rail contamination at the appropriate times. However, to enable remedial action to be taken in areas affected by exceptionally low adhesion, your cooperation is needed. Report these conditions to the signalman as soon as possible in accordance with the Rulebook Appendix 1 instruction. You're not expected to report normal low adhesion brought about by conditions that other drivers should already be aware of, such as the onset of rain or drizzle, or locations regularly affected by low adhesion. The basis of the instruction is to warn drivers of newly arising locations that they're unlikely to know about, or where you've had greater difficulty than normal in stopping at a known low adhesion location even after adjusting your driving technique. In this case, it could be that the effectiveness of an earlier remedy, for example sandite, is wearing off.
A report of extremely low adhesion conditions in the Chorley Wood area.
Once you've reported the location, drivers of following trains can be warned, enabling them to modify their driving technique in good time. In addition, action can be taken to inspect the site and remedy the situation. Remember, forewarned is forearmed. We've already seen that driving technique is of paramount importance. When you've reason to believe that you might encounter low adhesion conditions, you must adapt your driving technique. There will, of course, be different braking techniques depending on what type of train you're driving. For example, whether it's high or low speed, tread, disc, or mixed brake, freight or passenger. Learn to read the conditions and react accordingly. It's your skill and judgment that's the vital factor. Here are some fundamental principles to remember. Make your brake applications earlier and lighter than normal, just as you would in your car on an icy road. If you're driving a disc-braked multiple unit or locomotive haul train with WSP equipment, don't release or fan the brake when there's WSP activity. If your train comprises tread-braked vehicles, manually control the brake to avoid locking the wheels until the safe braking distance has been reached, when the maximum brake cylinder pressure necessary to stop the train should be applied. Short trains in particular require greater care. If you unexpectedly encounter low adhesion, you might not have the chance to modify your braking technique. In this case, make a full service application immediately and leave it on until the speed is dropped or adhesion has been sufficiently regained to stop normally. Your training and experience will help you determine what's appropriate, but make sure you know the best braking techniques for the types of train you drive. Don't leave it until after an incident to find out. Remember, put safety before punctuality. We've already talked about WSP equipment on disc-braked multiple unit and locomotive haul trains and how it's important to allow this equipment to operate in low adhesion conditions. Experience of incidents last year shows that many drivers still have a tendency to release the brake when WSP activity starts, contrary to braking instructions. There's a wide range of WSP equipment fitted to disc-braked vehicles, ranging from the older electromechanical systems acting independently on each axle to the latest vehicle-based microprocessor-controlled systems. They all have one aim in common: to detect low adhesion on each axle down the length of the train and to make the best use of the adhesion available. This is achieved by rapidly adjusting the braking effort on each axle to the maximum that the rail condition will sustain. It's important to realize that low adhesion conditions aren't constant along a stretch of track. They rise and fall randomly. WSP reacts very quickly to every change, adjusting the braking on each axle to obtain the maximum possible braking effort at any instant in time. You can't necessarily judge what's happening from the indications you see and hear in the cab, as these only relate to the locomotive or leading vehicle, and not what's taking place down the length of the train. As a driver encountering low adhesion, can you ensure by manual control that the braking effort applied to each individual axle is the maximum the rail can sustain? In 1992, low adhesion tests were conducted to demonstrate the ability of the WSP against manual control by the driver. The results showed that under full service braking, WSP could consistently stop the train in a shorter distance than was possible by the driver manipulating the brake. With each new generation of WSP comes improvement in its performance. Most recently, modern microprocessor-controlled WSP has led to the virtual elimination of all-wheel lockups, even in exceptionally low adhesion conditions. This has been achieved by the development at BR Research of a test rig named Whisper, the Wheel Slide Protection Evaluation Rig. Whisper uses a powerful computer to test real WSP equipment, evaluating its efficiency in accurately simulated low adhesion conditions. Repeating the same tests over and over again, minor changes to WSP software can be assessed until optimum performance has been determined. Let's have a look at Whisper in action. What you're seeing now is a test run of an unmodified WSP rack under exceptionally low adhesion conditions. The white trace represents the actual speed of the vehicle, while the purple trace represents the speed of the vehicle as determined by the WSP equipment. The red, blue, green and yellow traces show the individual speeds of each of the four axles on this vehicle. In addition, there's a velocity meter indicating the actual speed of the vehicle and a deceleration meter. What is immediately obvious is that the actual speed of the vehicle, the white line, is not dropping as quickly as the WSP thinks it is, the purple line. This is because the WSP normally determines the train speed by comparing the speeds of individual axles. With all four axles being subjected to controlled slide by the WSP, the system can no longer rely on axle speed comparison, and so has to calculate the train speed. As you can see, this calculation doesn't match what's happening in reality. At this point, the WSP thinks the vehicle is almost stationary, and so it switches itself off. In fact, the vehicle is still travelling at 60 miles an hour. This results in all axles locking. The four axle speed tracers have dropped to zero. The vehicle is in an all-wheel slide. In these exceptionally low adhesion conditions, Whisper has calculated that the vehicle took 1,869 meters to stop from 75 miles per hour under a full-service brake application. Now let's run the same test under identical rail adhesion conditions, but this time with software controlling the WSP modified to its optimum configuration. This time you can see that the brake on one of the four axles, wheel set 1, is momentarily released at intervals of approximately 10 seconds. During its release, it returns to full speed and is thus able to tell the WSP what the actual train speed is. This information is used to reset the calculated speed, matching it more closely with the real speed, keeping the WSP operative and avoiding wheel locking. During this test, the train took 1,586 meters to stop from the same speed of 75 miles per hour, reducing the stopping distance by 283 meters, an improvement of 15% and without wheel damage.
Again, you should remember that these are extreme conditions which would normally be treated by the removal of contamination or by sanditing, but they serve to demonstrate the improvement that can be gained through upgrading of WSP equipment. Unfortunately, it's not simple to modify all WSP systems in this way, particularly the older types not controlled by software. The Whisper tests are helping to solve some of the problems of low adhesion, but there are no magic solutions. What we need is a range of measures, both to avoid rail contamination where possible and to manage it more effectively when it does occur. In March and April of 1995, British Rail held 2 seminars to seek the views of drivers, signalmen, engineers and managers in determining the nature of the problems and finding ways of moving towards solutions. The first seminar was addressed by Sir Bob Reid, then the chairman of BR, and many important issues were raised. These and other adhesion-related issues will now be tackled by a newly formed BR and Railtrack Adhesion Working Group. There are plenty of issues to look at, including technical on-train systems, reporting procedures and consequent remedial action, driver training, detecting and predicting low adhesion, to name but a few. You'll be briefed on the group's progress in due course.
2 trials are already underway, evaluating sanding equipment on South West trains Class 159s and Thames trains Class 165s.
We're rapidly approaching the next autumn leaf fall season, so I hope you found this program helpful. Here are the main points again. Low adhesion can occur all year round due to various natural conditions or industrial contamination. Exceptionally low adhesion is rare and is normally associated with crushed leaves on the rails during autumn. There are no magic solutions to problems of low adhesion. We need to tackle them with a range of measures. Make sure you know where and when low adhesion conditions are likely on the routes you work over. Watch out for the telltale signs: wheel spin, erratic speedometer readings, the onset of particular weather conditions. Make sure you know the best braking technique for each of the types of train you drive. Adjust your normal technique. Brake earlier and lighter.
If you drive disc brake trains with WSP, let the WSP operate. Don't try to beat it by releasing or fanning the brake. Report serious or prolonged wheel spin and monitor for serious wheel flats. Finally, report exceptional rail conditions to the signalman as soon as possible. Remember, safety before punctuality.